Hi everyone, so we're going to finish up chapter 7. There are some additional sections in chapter 7 I want you guys to read, specifically on the photodiodes, but we're going to basically wrap up with 7.9, which is just some additional circuits that operational amplifiers can do, and this will actually also lead us into both our next module, which is going to be on modulation, demodulation, and also comparators will lead us into, we're going to see some parallels with digital electronics. And hopefully I can highlight those as we go along so that it reminds you that, oh, this is actually how our computer is based on these transistors slash operation amplifier that we're able to play around with in the lab. Okay, so let's just talk about what comparators are. So comparators, like the name sound, compare two things. Hopefully that makes sense. Okay, you can do this pretty simply because, right, let's say you have a voltage VCC, let's say that's plus 5 volts. And then if we're using one of the op amps that doesn't require split supply, let's say, right, we can put this to ground, right? For the LF411, you do need a negative 1.5 at least. But for the LM358, you do not. So what happened is that whatever your input is, right? Let's say your input, your V plus is 1 volt, your V minus is 0.9 volt, right? What happened is that this difference of 0.1 volt gets amplified by this A, right? And A is like, 100,000 or something like that. But your output is not going to be 100,000 times 1 volt, right? Because you don't have a 1000 volt power supply, your output is going to be 5 volts. So whenever V in is bigger than V minus, right, the V out will rail to VCC, right? Whenever V in is less than V in plus is less than V in minus, right? That means the non-inverting input is less than the inverting input, right? Your V out is going to rail to VEE. So in this case, it's going to be 0. It's kind of nice, right? Because then you're just comparing those two numbers. Which one is bigger? And that's what this does. For example, right? What I'm going to do is I'm going to add a little bit more to this, right? Let's say I have a little voltage divider here. I'll do this. Same coding. Right. Okay. This is to the 5 volts. Right. I'm going to put another 5 volt here. Put the line here. Right. Let's make this a 5K. Actually, I want this to be 4K, 1K, just to some nice easy number. So this is a 1/5 voltage divider, right? If you have 5 volts here, then it's going to provide you a constant 1 volt here. So whatever your input here is, right, Vn, right, that means it's just comparing Vn to 1 volt. Is it bigger than 1 volt or less than 1 volt? If it's bigger than 1 volt, your output will be 5. If it's less than 1 volt, then your output will be 0. Okay, so these are very nice, right? You can even buy specialized comparator like this. These are called LM311. The experiment we actually use, let's talk about that later. The way this works is that basically what happened is that one of the transistor goes to ground inside the op amp, and all you have to do is basically connect this to a single voltage power supply. There's this pull-up resistor because what happened is that what it does is actually does an inversion. So you actually want this to be pulled up, right, when Vn is bigger than 0. Well, 0 or whatever, you can set this to whatever you want. It doesn't have to be 0, okay? And then the output is 0 if Vn is negative in this case. Or in, that's my case, right? Instead of putting ground here, you can put this, you can set up a voltage divider to set this voltage to whatever you want, okay? In fact, this is what we do on our neutrino experiment. You can see the board here. I probably should have just zoomed into one of these and show you guys. Okay, so these are LM411, slightly faster version of these comparator. And what happened is that this thing here, you might see, I think that you guys have this version of it, but this is a potentiometer. Okay, and what this circuit does is basically exactly what you have up there. You have some Vin, okay, and this is biased to with a resistor. So this is the non-inverting input, inverting input. So low resistor to, I think this runs on 5 volts. Okay, and I think this is where this potentiometer sits. So that's what the potentiometer is. There's an additional resistor here. Okay, in fact, I think it's the one on the right. Sorry about that. Okay, it's up here, right? And then you can change this potentiometer so that it has a very fine voltage. We set these at about 5 millivolts. Okay, so the reason we do this is that if we see this is designed to detect signal from a photomultiplier, meaning it's just a signal from light. And what happens is that as the signal comes in, it'll pulse, right? If we have something, the voltage is function of time, right? It'll give you a pulse, and these pulses are like maybe 10 millivolts in size. And then, right, the comparator, since this is set to 5 volts with a threshold of 5 millivolt, which is actually not that low, it's up here, right? When it crosses this, it goes straight up to 5 volts. And that way we can, digitize this signal basically, as opposed to trying to deal with this tiny 10 millivolt signal, okay? And this is one way a comparator is used to just tell you, oh, is there a pulse or not, okay? But this gets you into trouble if you have the simple version like this. You might even see this here. There are additional, no, well, black, green's not going to work very well. We'll go back to red. Additional resistors and capacitors here, right? It's not just the ones that that potentiometer, right? Okay, so what are these things for? This is to prevent oscillation of the signal from triggering the comparator multiple times. And the method for doing this was some guy whose last name was Schmidt, and that's why it's called a Schmidt trigger. So the effect comes from the fact that, well, your signal is not going to be exactly a straight line, so there's some little noise in it, right? And then when this noise happens, it's going to cross that threshold like thousands of times, okay? Because there's some high frequency noise, right? Well, maybe not thousands, hundreds of times, okay? Then what happens is that basically your comparator output switch up and down, up and down, up and down, a lot. And you don't want that, right? Because, right, that confuses your, what you see afterward. And also it's not good to ramp your op amp up and down like that all the time, okay? This is known as the Schmidt trigger, okay? And it uses a positive feedback loop. So this is we're gonna connect our V out to the non-inverting input instead. Okay, I'm gonna do Control Z to move that back. Okay, stop it. Okay, there it goes. Stop it. Stop it. Yeah, right. So this is known as a positive feedback loop because instead of going to the negative non-inverted, the inverting terminal, we're going to go to the positive, right? V in positive, the non-inverting input. Okay. So the way this works is that it buffers, right, the threshold. So when you cross the threshold from the low end, okay, so low to high, it has one threshold. So maybe that's, 5 millivolts. But then you can pick these resistors so that it gives you a little buffer of maybe an additional 5 millivolts. So when it crosses from the other direction, where it goes from high to low, right? Because if you zoom into this, yeah, I wish the book actually drew this a little bit more detail. So I'm going to redraw it just to show you guys how useful this is. So I'm gonna exaggerate what the book has, okay? Right, so like this. Okay. And if this is your initial threshold, right? This crossing here, right, is gonna trigger the comparator, right? But without this buffer zone, the second downward peak also triggers the threshold, right? And this third one also triggers the threshold. You don't want that, right? Because this is just noise, because this is just a single crossing. So what you do is you build in a buffer. I probably exaggerated the noise too much. Let's do that. Right. So you want to build in this buffer, right, where this noise is no longer triggering your threshold multiple times. And the way you determine that, right, is by setting these resistors so that you have I think this is going to be set at whatever 1%, yeah, 1% of whatever your power supply is. Okay, so that way you get a clean comparator signal as opposed to this up and down all the time. Okay, so let's talk about another circuit. This is known as a gyrator. This is actually known as a clock chip, a clock. And you may be wondering, like, how do you make a clock out of an amplifier, right? Okay, it's an oscillator. Also, yeah, gyrator, oscillator, they're all the same thing. Actually, I think gyrator is a little bit different. No, so yeah, oscillator or clock. Okay, so don't forget about gyrator. Okay, so let's connect this op amp up like this. It's a little odd. Okay, so you have a capacitor here, and then you're connecting the output to both your output to both your inverting input through this resistor R, and through the non-inverting output through this voltage divider here. Okay, they're both 10K, so it's a 1/2 voltage divider. So why 1/2? Okay, so this will create something that it's kind of interesting. Notice that there's no VN. We don't put an input in here. This thing, once you power it up, it just does this thing by itself. You don't have to have a function generator or anything like that. In fact, the signal from your function generator are probably created by this. Okay. Okay, so how does it work? Okay, so the op amp charges the capacitor up, right, because it's running current through this. Okay, and since V minus cannot take it, V in minus cannot have any input current, all the current goes to the capacitor, right, ideally. Okay, as the capacitor charges up, okay, when V out is bigger than 0, okay, then what happened is that when V out reaches this VCC over 2, which is what this voltage divider is doing, right, it switched to discharge mode because now it drives V out to negative instead. Okay, whatever the negative voltage supply is. Okay, this is sort of a neat system here. Okay, so the picture of this is that, well, if you have a split power supply, you get a Vmax and you get a negative Vmax. What happened is that the signal basically oscillates between negative Vmax over 2, and this 2 comes from the fact that you pick a 1/2 voltage divider. You can pick that to be whatever you want. Okay, and then it goes up and down, and it just kind of oscillates up and down because what's happening is that you're charging and then discharging that capacitor, charging, discharging, discharging, discharging. And the switching is done because, right, once that capacitor reaches Vmax over 2, right, or VCC over 2, right, it'll switch the output of your op amp to negative. And then once it reaches below negative Vmax over 2, right, it switches back to charge. So it's charges, discharge, charges, discharge. You can actually see this pretty easily here. So this is the voltage output of your operation amplifier here, right? It just goes up and down as a square wave, while the V2, which is taken between these two capacitors, right, is actually the little oscillating saw wave. Okay, and you can do this very interestingly, and this is actually going to be what's used to generate what's known as clocks in digital electronics. I did a bunch of derivations in order to show you guys how to get the the period of oscillation. So maybe I'll show you guys how to do that on like a little homework problem. I think that'll be more interesting because there's just a lot of algebra steps. Okay. All right. So the last thing I want to talk about is photodiodes. So photodiodes are diodes that absorbs light and converts that light into electrical signal that we can see. Here's some examples of them. There's those little glass ones. There's also these are also photodiodes. You can recognize them because it has this little black surface to them. The reason it's black is because it's very photo absorbent, right? Black things absorbs light. Okay, so the way this works is that when photon, right, hits the depletion region, right, it has to hit that. Okay, what happens is that through the photoelectric effect basically generates a electrons inside your depletion region, and this electron is free to move because it's actually not bound to any atoms. So that actually creates a current. So what happened is that unlike just regular material, there is a electric field right inside this depletion region, and this electric field basically drives electrons out of one end of your diode. Okay, so this is kind of interesting. You can just have a little diode somewhere, and then if light hits it, you generate current out of it. This is basically how you can generate electricity from solar panels also. Okay, so one photon creates one electron, right, due to the photoelectric effect. In fact, not all the photodiodes are usually designed to have an optimal absorption at a particular wavelength, and this is known as the response function. Okay, so if you have a 400 nanometer wave, which is a very high, basically a blue light, right, for this particular photodiode, it has a very low response, meaning you get a very small amount of current per watts of power that you provide to it. Okay, so this peaks right at maybe about 950 nanometers, which is actually near infrared. So this is probably some near infrared sensor that someone built. So what we can do is we can estimate how much current that we get out of a photodiode if we know the response, right? The area, how big that sensor is, right? Because every photon that hits it gets converted into an electron. Okay. So going back to just kind of converting power to photons, right? So we think about like an incandescent light bulb, right? 100-watt incandescent light bulb. Only 10% of the energy actually gets made into photons, because gets made into like the visible spectrum. Okay, a lot of it actually goes into infrared, which is what we don't see. Okay, so if we're 1 meter away from a light bulb, right, the intensity, okay, this is going back to general physics definitions, right, is the amount of power that you get per area. So I'm going to draw this, right? You have a little light bulb here, right? The light goes out, right? The intensity, if you have a 1 meter by 1 meter sensor here, the intensity tells you how much power you get per unit area. Okay, so since we're dealing with, like, let's say an incandescent light bulb, right, 100-watt light bulb, and only 10% of the energy goes into generating visible light. Okay, the power coming out of the light bulb in the visible band range, right, is actually only 10 watts. Okay, the area of this, okay, since this is a growing sphere, right, gets bigger and bigger, right, the intensity actually goes down as 1 over r squared. Well, r squared, I don't know why I use m here. Okay, therefore, right, if you place that sensor far enough away, you actually get decreasing amount of intensity. Yeah, I don't think that's relevant here. Okay, so let's say the size of the sensor, right, is 3 millimeter by 3 millimeter. If you punch this in your calculator, the area of the sensor is about 10 to the minus 5 meters square. So we want everything in SI units. So the power you get is actually about 10 to the minus 5 watts. Okay. So if we're just, have a photodiode about a meter away from a light bulb, right, we're going to get about 10 to the minus 5 watts of energy onto that little photodiode. Okay, so 3 millimeter by 3 millimeter is pretty small. Okay, all right, but we want to convert that to current. So how many photons is that? Okay, so from your modern physics class, the energy of a photon is equal to h times f, right, where h is the Planck's constant and f is the frequency. We want actually the wavelength version of that because it's a lot easier to deal with things on wavelength. You can convert f to wavelength by just c over lambda. Okay, and therefore, right, h is about 2 times 10 to the negative 25 joules meter. So if you put in 500 nanometers, let's do that, 10 to the 9, negative 9, right? That's about the wavelength of green light. Okay, 500 nanometers. So that means the energy that we get out of that per photon is about 4 times 10 to the minus 19 joule. Okay, so if we take the ratio of these, okay, right, how many photons are there in 10 to the minus 5 watts of energy? Okay, the number of photons that we get per second, because this is a power, so this is joules per second, okay, it's going to be 2.5 times 10 to the 13 photons. Okay, and if our photosensors are 100% efficient, which usually they are not, okay, the amount of charge that you get, right, right, because each of these is 1 electron, right? Okay, the charge of 1 electron is negative 1.6 times 10 to the negative 19 coulombs. Sticking to the SI units, you multiply that together, you get about 4 times 10 to the negative 6 coulomb. Okay, so that means, right, the current, this is not 1, the current that you get from a light bulb that's about a meter away from a small sensor like that, it's going to be about 4 microamps, right? Because that's the number of coulombs per second that you're generating. Okay, so what you want to do is actually, it's a small signal, right? A microamp is pretty small. You want to send this to be amplified as soon as possible. And this is where a transimpedance amplifier comes into play. Okay, a transimpedance amplifier is basically a photodiode, okay, that's connected to the the inverting input through a large resistor and a moderate capacitor. So that's going to pick basically how much how does it change with frequency. Okay, at low frequency, right, what we get, basically the capacitor is an open, right? You get the current that you're generating times RF. As frequency increase, right, these two are parallel to each other, and this basically becomes a little low pass filter. Yeah, okay, and the Z decreases. Okay, we can calculate the bandwidth of this amplifier, right, because that's basically the F3 dB point. Okay, so if the bandwidth is above the frequency of the signal you're trying to measure, you're going to start losing signal. Okay, so for example, if you're taking a phone video, well, they used to be about 75 hertz. Now we're doing like 120 hertz videos actually, right? on your phone, right? You want the bandwidth to be substantially higher than that. So maybe you want the bandwidth of your photodiode to be 200 hertz, okay? And that's a pretty slow amplifier. But if you're counting photons, for example, in a quantum optics experiment, right, you want to be able to read out your sensor every nanosecond, right? You need a bandwidth of 8 gigahertz, okay? And the problem is that, as you see, right, on this little equation here, right, the bandwidth is inversely proportional to your RF, right? Bandwidth, right, goes down if RF goes up, right? But your gain goes up if your RF goes up, right? So you're going to have to decide when you're designing these photodiode transimpedance amplifier, right? Do you care about gain more, or do you care about speed more? Okay, so so a lot of these design are weighing the different aspects of what's important to your particular experiment. So that's all for today. So I will post this and get the homework out to you guys as soon as possible. Okay, thank you.